Thank you very much for the introduction and for the invitation, and also for the opportunity to speak on Wednesday so that I can torture the maximum number of people with the Motivic spectral sequence for the affine line of evaluation ring. All right, hopefully we'll get there. So anyway, yeah, so this is a project about Motivic cohomology of general schemes, so not something like smooth over a field or maybe not regular or something like that. And it's one canonical definition of Motivic cohomology for these guys that I will explain. So there's a key feature is that it's A1 invariant. I don't want to say that's a plus or a minus. That's, I guess this depends on your taste. But today, well, for this hour, everything will be A1 invariant eventually. Okay. So as I said, I want to do A1 invariant things. And A1 invariant cohomology theories, they have a natural home, and that's the Motivic stable homotopy category. So I have this SH of something, and you can stick in anything you want. Mostly, I mean, I will stick in schemes, but if you want, you stick in stacks or I don't know what else. So this is a functor. We start with a scheme, and it's going to be contravariant, and out you get a category. And of course, I mean an infinity category. So this has a lot of nice properties. So these categories here, they're presentable, they're stable, they're symmetric monoidal, which I guess is not a property, but whatever. Okay, and so this is somehow the natural home of that's the natural home of Motivic cohomology theories. Or I mean, if I turn this around, it's a factory for Motivic cohomology theory. So if I have a spectrum in here, then this gives me a cohomology theory in whatever sense. Okay, so this is somehow my factory for cohomology theories. Okay, and so first of all, I want to explain what I mean by that. So let's say I have some.
Just a quick question. So
Go for it.
This functor lacks symmetry model.
This functor, I guess. Okay, so suppose I have some Motivic spectrum. So I need, of course, to work with the Motivic spectrum over some scheme, and I will use the most universal scheme there is, which is the spectrum of the integers. Okay, and so out of this, I will extract the cohomology theory, which is defined for every scheme whatsoever. Okay, so I extract this thing. Somehow more concretely, which I denote by E underline. Oh, stop. Okay, so this is now going to be a functor again from all schemes, and it's contravariant, so it's a cohomology theory. But this time I spit out not a category but a spectrum. And what you do is, of course, the following: you take some scheme X. And I send it to, well, I do the following thing. As I said, this is going to give me a stable infinity category, symmetric monoidal stable infinity category. So I can get a spectrum by doing some kind of internal mapping spectrum. And the source is going to be the unit, right? So this is one object which I have in every symmetric monoidal category. And then also I have my E in SH over Z. But of course, this SH thing is a contravariant functor, and everything has a canonical map to Z, so I can just pull it back. So I just denote this by E restricted to X. Okay, so that's the spectrum. And so for every scheme, I get a spectrum, so I get some cohomology groups. I guess I can soup this up a little bit, which is that, I mean, you know, Motivic cohomology tends to have these two indices. And here's the spectrum, so it's only one index. But I can fix that, okay? So I can record the other index too. So maybe let's just put another Z here. And just to be clear, Z just as a set, not as a category. So in order to do this, I will twist this thing here by some Motivic spheres. So I put some bullet here, I suppose. And I put some. Okay, there's some convention of how to twist it, and this is how I will twist it. Okay, and so if you take any Motivic spectrum, you get out this cool data for any scheme. So I guess I should give you some examples of what Motivic spectra there are. I mean, okay, oops, what is going on? Okay, so inside SH of Z, if this factory is supposed to do anything, there have to be interesting things. And of course, well, you have the sphere spectrum, and you could use this, but I don't know very much what this is going to mean. There are other things. So there's something called the algebraic cobordism spectrum, which is somehow very canonical and important. But that's also a story for another talk. But now we get to something which I will actually talk about. So there's the algebraic K-theory spectrum. So there's KGL. So this is actually 2-1 periodic. So this shifting thing here is kind of useless. And over smooth schemes over Z, this guy represents algebraic K-theory. So then you can pull it back and you get whatever. But OK, so this guy exists. And I mean, most crucially for my talk, there's something which we call HZ. Okay, so this is what's called Spitzweck's Motivic cohomology spectrum. Okay, and so he cooked it up in such a way that for smooth schemes over Z, this represents higher Chow groups. And so the fact that there's a chance of doing this, so there's a lot of people who have to be credited with making this work. So maybe I will put here Geisser, Levine and Bloch, I guess. Probably Voevodsky has his fingers somewhere in there, I'm not sure. But OK, so somehow these people managed to construct this guy, and it means higher Chow groups for smooth schemes over the integers. And so now you can stick it into my factory, and you get out a theory for every scheme, right? Any scheme that you want. And so the main aim of my talk is to figure out or to explain what happens if, well, you take some random scheme and not something smooth over the integers or some Dedekind domain. Okay, so the main question is this. What is HC underline bullet? Okay. And maybe I will begin with an example. So what is the best possible answer that we could hope for? And this is what happens for, let's say, what happens with K-theory. Okay, so if I take KGL, and I do my underline bullet thing. So I mean, as I said, it's periodic, so the bullet is kind of pointless. But so one can prove that this gives you homotopy K-theory. Okay, so there's a sheaf of spectra, or a pre-sheaf of spectra called KH, which is you take non-connective K-theory, and then you do the singular construction. And it turns out that these two things are the same. I guess this is due to Szysinski. Okay, so that would be the best possible answer. You do this abstract machine, and you get out some well-known guy. Now, I don't think there's a well-known definition of Motivic cohomology for an arbitrary scheme, so we can't quite hope for this. But so ideally, what I can do is I can give a reasonable or maybe more reasonable looking definition of Motivic cohomology and then say it's the same as what comes out of this machine. So that's what I'm hoping for. Or, well, that's what I will do. So we get rid of this. So in order to do this, to even have a chance, I first have to tell you some more things about some more properties and structures on these underlying theories that you can get. So we have the following structure on this E underline bullet. And so the point is that this is a spectrum in somehow the P1 direction. So what this means is that if I take this E underline bullet in degree I plus 1, and you take the P1 loops of that, okay, so that's an operation which I can do with any pre-sheaf of spectra. And then one is given an equivalence of this guy with the thing in degree I. Okay, so that's some extra data, which I have not explained where it comes from, but one can construct it. And if you definitely you will have to record this data if you datum if you want to describe what happens. And beyond that, these things also satisfy a bunch of properties. All right. So the first property is not a big surprise, which is that this is A1 invariant, right? So E underline bullet of X cross A1. There's a natural comparison with E underline bullet of X, and that is an equivalence. So as I said in the very beginning, everything will be A1 invariant. This is sort of built into the theory from the start. And the other also pretty obvious property is that these are all Nisnevich sheaves. Again, because basically the way the Motivic homotopy category is built, this sort of Nisnevich sheaf property is built in from the start. And so there will be two more properties, 4 and 5, but I want to skip them for now. I will say something else first. But also, before I even get to this, I want to point out that this Nisnevich sheaf property is very useful for many things. And one thing is that I've written schemes, right, with 0 assumptions. And maybe you're thinking, well, technically he means QCQS or I don't know, something. But the point is technically I mean nothing. Because, I mean, if you're a sheaf, then of course you're determined locally, right? So if I want to understand what this does on any scheme whatsoever, I can immediately restrict to like affine schemes or QCQS schemes. So this allows me to work only with, let's say, QCQS schemes. Determined on schemes. Okay, so this is getting a little bit more reasonable. Okay, so why am I telling you this? And the fact is that these properties 1 to 3 essentially characterize completely this underlying bullet construction, which I guess is not very surprising if you know the definition of SH, because basically it's things which satisfy 1 to 3, but I mean sort of for smooth things over a base. But if you record all of them at the same time, this is what happens. So the fact is that 1 to 3 characterize this E underline bullet. So I can make this more precise. I can look at the category of P1 pre-spectra on all schemes. Okay, so by this I mean sequences of pre-sheaves of spectra together with the kind of data here with a map like this, which may or may not be an equivalence. Okay, so the reason why I want to look at this is, of course, this allows me to record all the data that I claimed is necessary, and everything else is a property. And then I can forget down to P1 pre-spectra on smooth Z schemes. Okay, and there's a left adjoint, some left Kahn extension procedure here, which I denote by LSM. Okay, left Kahn extension from smooth schemes. That's somehow fundamental operation in this business. And you see the classical or the usual Motivic homotopy category of Z. It sits inside this category of pre-spectra, right? Basically, it's the it's the object satisfying 1 to 3, essentially by definition. Okay, and so if you start with some guy here, you can left Kahn extend it to here, and now it may or may not satisfy any property. But I'll just ask for it to satisfy 1 to 3, and then that's the answer, right? So E underline bullet is the initial object under L smooth E satisfying 1 to 3. So what do you need to do if you want to figure out what HC underline is? Well, you take your higher Chow groups and you take your model for it. I don't know, some sort of Bloch cycle complex over Z. You left Kahn extend it to arbitrary schemes. You make it in this Nisnevich sheaf. You make it A1 invariant. You spectrify it, and then that's the answer. Okay, so that's the end of the talk. Right. So I want to make it more reasonable than that. But in principle, that's what we're after. So I want to have another example. So I want to discuss this KH guy again. Where is it here? Okay, so one has the following interesting formula, which is that this KGL underline bullet is actually the cdh sheafification of the left Kahn extension. Okay, so it's given by this. So that's a very surprising formula to me, but apparently that's a true fact due to a number of people. So I guess I will put here Bart Lurie. No, wait, I want to put Lurie Matthew. And so what I mean by this reference is the fact that if you take connective K-theory and you left Kahn extended from smooth affine schemes to affine schemes, you get back connective K-theory. Apparently that's a fact. And then, is it Bart Lurie? But why doesn't Akil have to do with this? Well, I will put what Mark says, because he knows. So, oh no! Right, yes. That's the version that I know about. In any case, this is a fact somehow. And then I put Kelly Morrow. And what these guys explained, that the apparently well-known fact that K-theory of valuation rings is A1 invariant and connective. And then you put this together with Elmanto, Oyoa, Iwasa Kelly, and I guess I also put Szczynski here again. I don't know. So the thing is that these guys, I guess, proved that the cdh top was hypercomplete in this relevant setting. And okay, if you believe all of these things, you get out this fact. And Mark is looking very skeptical, which is scary, but I was told this is a fact. I hope it's correct. So there's something, okay, so there's something a bit strange going on here, right? Which is that I put in a cdh sheafification. So that from what I've told you so far, there's no, this KGL underline bullet has no right to be a cdh sheaf. Why would it be? But somehow this is part of the Motivic magic. So this follows from the six functors formalism, in particular from proper base change. So if you take this E underline bullet, for any E is always a cdh sheaf. I guess I wanted to put this here. Okay, maybe this is Szczynski-Diglis. So that's our first clue. This always happens. So the cdh topology seems to be relevant to this whole business. And 4 is that these E underline bullet guys are always what's called finitary. So if you take a co-filtered limit of QCQS schemes with affine transition maps, then this cohomology theory will convert this into a filtered co-limit. And this means that instead of thinking about QCQS schemes, I can even think about finite type Z schemes, which is maybe more comfortable. Something like this. All right. So now I have enough. Is better? So now I can state the main theorem. Which is, of course, some version of an answer of the question, what is this HZ bullet underline? All right. And the theorem is that it works exactly for the Motivic cohomology as it works for KGL. Okay, so it says that HC bullet, this is the cdh sheafification of the left Kahn extension of HC. Okay, so there's a canonical map from L smooth HC into HC bullet, and this is also a cdh sheaf, so it factors through the cdh sheafification. So there's an obvious map here for some value of obvious, which I claim to be an equivalence. And of course, equivalently, right? So it's the initial guy under this which has all the properties. So equivalently, this is saying that if you do this construction here, what you get is A1 invariant and it's a P1 spectrum. This is what I have to prove. So this guy here okay, so this is still quite abstract because you have this left Kahn extension and then take some cdh cohomology. So hopefully I will present some other answers which are maybe a bit more helpful in some situations. But also I want to point out this is not completely useless. Okay, so one has the following corollary. So this is maybe something more internal to Motivic homotopy theory. So if you don't really know what the symbols mean for the next 3 minutes, don't worry. I'll get back to Earth soon. But the thing is, if you take any scheme X, then I can look at the sphere spectrum, let's say over X, right? So this is all going to happen in SH of X. And so Voevodsky devised this filtration called the slice filtration, which is some sort of replacement of the Poznikov tower. And he expects that under some assumptions, if you do this filtration to the sphere spectrum and you look at the analog of pi 0, which is called the zero slice, then you should get out the Motivic cohomology. Okay, so he did this at a time when maybe Motivic cohomology over general basis was not defined, and also everything else was maybe not super well defined. But so he asked if this is true, and maybe under some assumptions. And the answer is this is always true under no assumptions. So that's, I think, kind of neat. So let me quickly sketch the ideas of this proof. So what you do is you look at, this HZ guy is a particular ring spectrum, so there's a canonical unit map. And then there's some fiber here. And notice that everything that we do is stable under base change, basically by definition. And so what's going to happen is that this HZ and this 1, they are effective spectra. And the fiber is 1 effective. And all of this you can find in the appendix of the norms paper with a mark, where we basically say these things reduce to the case of fields, and for fields the other mark has proved it. So I should have written mark here, but anyway. So you get this, okay? And so what this tells you is that they have the same zero slice, but it is not immediately obvious that this is in fact the zero slice itself. So it remains to prove, I need to prove that the 1 effective cover of HZ is 0. But this is equivalent to saying that if I do this HZ underline bullet construction, I look in degree -1, I get 0. Okay, so that's basically the definition of what this F1 means. But now look at my formula. Okay, so what's HZ underline bullet -1? You take whatever was in degree -1 and you left Kahn extended and you cdh sheafify it. But one knows that over a Dedekind domain, the -1 part is 0 because basically Marcus has proved this from the beginning. And yeah, so this is true because F1 HZ over Z equals 0. Okay, so in the case where the left Kahn extension is very easy because you start with 0, you end up with 0. It's a not obvious statement, but this one can prove. So, okay. There are more things which one can do here. For example, you can look at the slice filtration of KGL, and you learn that it always, well, I guess for QCQS schemes and finite type schemes, it always converges, but the layers are always given by Motivic cohomology, and so on and so forth. So I think it gives some interesting results.
But isn't this requiring, I mean, don't you need to know that the slice filtration behaves well with respect to this underlying dot?
No, I don't think so. I mean, it's not obvious that it does that.
Yeah.
So you mean for this here?
Yeah.
Well, but I mean, in order to know that F1 is 0,
Yeah.
I need to know this. These are basically equivalent, right? So F1 means maps out of X mesh GM into this guy is 0. So that's what the weight minus 1 thing is 0. And the claim is that the weight minus 1 thing is obtained by left Kahn extension from weight minus 1 on smooth schemes.
It's the weight minus 1 thing, which is nice. Yeah.
Yes, the weight minus 1. Well, this is also not obvious, but it's true for this guy. So in general, you would have to spectrify it, and so the could things somehow come from the higher weights and contribute down. And the assertion is that this does not happen.
So there's something special going on with that.
I don't know if that is special, but it's certainly not obvious. I guess it's probably special, yeah. Well, I mean, maybe it's true for all spectra, but the proof isn't going to work for all spectra. Okay, now I want to spend basically the rest of my talk trying to explain, well, how to prove this theorem, and also how to give a sort of more constructive version of this theorem, which is maybe more helpful sometimes. And in order to do this, I first have to tell you some facts about Motivic cohomology and KGL over smooth schemes over Z. Okay, so one of the main facts is that this KGL guy, this has the slice filtration. Okay, so somehow this F0 KGL goes to F minus 1 KGL, and it keeps going like this. And very generally, the co-limit is always KGL. I mean, for any spectrum, basically, this always happens. And then there's more terms here, F minus 1 KGL. And it keeps going in this direction. And a priori, there's no reason for the limit to be 0. Okay, so this is somehow the slice convergence problem already over fields, not obvious. And it definitely depends on the spectrum, so not clear. There's an F. Sorry, yes. There's a minus. Am I good now? Thank you. Okay, so this guy here has a name. It's called little KGL. And because this KGL, capital KGL is periodic, you can identify all of the other layers. So they're just going to be shifts. And these maps here are multiplication by the Barth element. All right. And so what one can prove is that you can prove that if you do KGL modulo the Barth element, you get HZ. And what you can also prove is that this KGL guy is what's called the framed suspension spectrum. Again, if you don't know what this is, don't worry too much about it. But what it tells me, in particular, is that it lies in the non-negative part of the homotopy T structure. And the important fact is that because this guy is in the greater than or equal to 0 part, of course, the other layers, they move into higher and higher parts. And this T structure is known to be complete. So it's also not obvious at all, but this is due to Strunk and Schmidt, I believe. And so it tells you that over Z, this filtration converges. Okay? And
Sorry, what's the subscript under the sigma?
framed. Yeah, there's something called the framed suspension spectrum functor. I don't want to explain it, but it produces connective spectra. It's the only thing that I will use. And from there, you can sort of boost yourself up. Okay, so what one knows more or less by construction is that if I take my hz I underlined and I restrict it to smooth schemes, then this will be, as a sheaf of spectra, this is I-connective. Okay? And so you combine this with the fact that you can compute, right? So this filtration converges. So in principle, you can compute whatever this little KGL guy is. You can compute it by comparing it with Motivic cohomology. And if you look at sort of how these things work out, what you learn is that KGL sort of is also connective. So right, what do I want to learn? What I want to learn is that this functor here so I look at KGL underline bullet, or I, restricted to smooth Z, and this is also I-connective. Am I doing this right? Yes, I think I'm doing this right. Okay, so previously I sort of knew that it was I-connective in the Homotivic homotopy T structure, but which is some abstract fellow, which I don't really know what it means. But now it is really just a connective in the sense of homotopy sheaves. And so maybe there's one more fact, which is that this, if I rationalize this guy, then one can construct Adams operations on this. So this is due to Ryu. And then the slice filtration splits. So rationally, HQ will be a summand of KGL Q. Okay, so maybe that's enough preparation about these things. So, I mean, yes. So I will have to tell you more facts about HZ, but I will do this as I go along. Okay, and so now the way that I'm going to prove the main theorem, which is still there, is basically I'm going to work one prime at a time and rationally and prove something for each of these parts. And note that if you're sort of eagle-eyed, you can already see that you can check this result one prime at a time and rationally. And so I will start with the rational part, which is this theorem that we'll call A. Right? And so this is about understanding HQ underline I. And the point is, this is an Adams summand of, or it's the Adams summand, or N, I don't know. Of KH rationalized. In particular, if I start with HQ, and I left can extend from smooth schemes, and I cdh-local, this guy is an A1 invariant P1 spectrum. Okay, and so this is basically very easy. I'm almost dare not write anything. The point is this HQ thing, right, as I said here, is a summand of KGLQ. So if you left Kahn extended and cdh-shifify it, it's still going to be a summand. Okay, so this thing here, cdh, smooth, smooth, HQ is a summand of LCDH, L smooth, KGL Q. But by the example from the beginning, if I had no Q here, I would get KH, and so I get KHQ. Okay, and I mean, obviously, a summand of an A1 invariant guy is A1 invariant, summand of a P1 spectrum is a P1 spectrum, and so we're done.
So shouldn't the statement be that this LCDH, LSM of HQ is an atom summand of HQ in particular? I mean, because you don't know, you want to show that it's the HQ underlying.
Maybe I remove the in particular and just assert all of these facts, or I'm not. You're right. I mean, when I wrote this, I was getting a bit nervous too. But anyway, this is supposed to be the trivial part, which is not very easy, not very interesting, but it's sort of foreshadowing, right? So if you try to analyze this thing, so you now already know what it is rationally, and it works very nicely, so you might be optimistic. I guess I was optimistic. Okay, and so the main thing is what to do one prime at a time. And so what I will explain in the talk is what you do in unequal characteristic. So I will work in schemes over Z1 over L. Okay, and I will analyze HFL. And I claim you do the following thing. So you do Motivic cohomology with the Z mod L coefficients. You underline it and you bullet and you look in degree I. And what you get is the following. So you start with the sheaf mu p tensor I. And then I consider the associated étale spectrum. Yes, definitely. This might happen many times more. Sorry. Okay. Now I étale sheafify this. So this is basically just étale cohomology with mu L coefficients. And then I truncate this. And I do not mean truncation in the sense of étale sheaves. If you want, this is just truncation in the sense of pre-spectra. But I'm immediately going to re-sheafify it, so I could have truncated in the sense of sheaves. But not étale sheafify it, I'm going to cdh-sheafify it. And I claim that this is also the same thing as okay, so I claim that this happens. And so in order to prove the theorem, actually I have to work with schemes over Z and not with Z1 over L. And basically you use similar ideas, but it will get much more complicated. And so I will explain this part, and then hopefully have some time to indicate what you do in mixed characteristic. I mean, technically speaking, this is completely subsumed by the mixed characteristic situation, which I have to deal with anyway, but I wanted to limit the amount of difficulty. Okay. Yes? I. It should be an I. Sorry, the dot, oh, now it's gone. Can I leave it like this? It's
bigger than or equal to minus I.
Yes.
Much better. That's the usual truncation. That's the homological.
Yes, yes, sorry. Cohomological in degree I. Yes. So that's actually the first step in the proof, that Okay, so the proof is now here. So the first step is that if you work with smooth schemes over Z, then this is true essentially by construction, but instead of cdh, of course, you put Nisnevich. Okay? So by construction, if I do this, HFL underline I restricted to smooth schemes over Z1 over L, this is L-nis of tau global, if we want, greater than or equal to minus I, L et al, mu L tensor I. Okay, so this is somehow some Bloch-Kato magic, I suppose, which is stuck into this by construction for us. So to step 2, is the following. So suppose I have some presheaf of spectra, schemes over Z1 over L, let's say finite type, to be safe, and up goes to spectra. And I will call this rigid if for every X is one of these schemes, and X in there is a point, what I want is that the value of F at the Henselian local scheme at that point is the same as the value on X itself. Okay, so that is some convenient property. And then the fact is that if this is the case, then F is Nisnevich locally left-Kahn extended from smooth schemes.
What do you mean by evaluating F as the Henselization?
Yes? What?
Only defined over finite time.
Right, but this is a object in here, and you take the filtered colimit. It's like a stock. Well, it is a stock. If so, L-nis F is equivalent to L-nis L-SM F restricted to smooth Z. Yes.
It looked like a subscript.
So the value at the Henselian local ring is the same as the value at the closed point.
Sorry, I just want to ask a silly question. So it's here you do a point, and that rigid also holds for Henselian pairs.
Well, I'm asking that it should hold, and I will make this conclusion. You could ask that it holds for Henselian pairs, and you would get a stronger conclusion.
It's stronger. It's strictly stronger.
I think it's strictly stronger, yes. Okay, so this is some fact. I don't want to prove it in detail, but I mean the idea is that you can check this on stocks because you have finite homotopy, locally finite homotopy dimension, and basically just if you have a Henselian local ring mapping to smooth schemes, there will always be a sort of cofinal system of essentially smooth schemes, which are Henselian local rings with the same residue field, and then the colimit is constant, and that's why this sort of thing happens. Okay, this is somehow some kind of trick. So the step 3 is that we know that étale cohomology is rigid in this sense, right? So L étale mu L tensor I is rigid, which I guess is due to Gaber. And therefore the same is true if I truncate. Okay, because I mean it's just some equivalence of spectra, and so obviously if I truncate them, they remain equivalent. And so what this tells me is that if I Nisnevich locally left Kahn extend this thing, I get this thing back, right? And
Sorry, Tom, can I ask a question?
yes.
So this step 2 works every time you have
It works if what?
Do you have finite cohomological dimension?
I guess I wanted to check something on stocks, so I need finite cohomological dimension, yes.
It's not invisible.
No, no. Right, so I was trying to prove that if I left can extend and cdh sheafify, I get the cdh sheafification of some explicit thing. I have proved that. But of course, I need to now prove that this is still A1 invariant and then P1 spectrum. Okay? So remains to prove. And then this thing here. Oops. Yeah.
Just back up a bit. You said step 3 and step 2 implies some identity. I didn't quite catch what the identity is. It's that identity.
I mean, I start with HFL on smooth schemes and I left can extended. And the question is, what do I get? Okay, so HFL on smooth schemes is this thing.
Yeah.
And now I left can extended. But this guy,
Oh, it's the same.
it looks, I mean, it's like the same thing, right? Because it's rigid. So this thing here is left can extended from smooth schemes.
I see.
Okay, so that the two things, left can extend and sheafify, and sort of the left can extension process I've now understood in some sense. And so what it remains to prove is that this pre-sheaf, or sheaf, which is defined now in all schemes, this is A1 invariant and it's a P1 spectrum. Okay, so the step 4. The step 4 is the cdh topos on finite type Z schemes is hypercomplete. Okay, so this is again Elmanto, Oiwa, Iwasa, Kelly. For Z? I see, okay. Well, Mark wants me to erase this. And I put Voevodsky, all right. But so what this means is that, again, I want to check something, and so maybe I will focus on this, and there will be some analogous argument for P1, right? So I want to check something, it's A1 invariant, and so I can check this on stocks now, because, well, I'm hypercomplete. So it therefore suffices to prove that H star, that the cdh motivic cohomology of A1 over V, right, where V is the stock, so V is the Henselian valuation ring, with coefficients in this. So this guy here I call FLI. Okay, so this should be the same thing as the cohomology of just V. So we are reducing from a general base scheme to a valuation ring. And now we need some more. This is not working at hand as all. Oh boy, oh boy. Okay, and so we need something analogous for P1, but I'm going to ignore this. So the next thing is that this thing here is going to be finitary for sort of formal reasons. And that tells me I can even assume that my V has finite rank if I want to. And which step are we now at? Yes, step 5. Step 5. Step 5 is that because this FP FLI guy, so it was, I mean, it was rigid before cdh sheafification. Okay, so let me just say is rigid. And this tells me that it satisfies something called Henselian V excision. Okay, so something that there's some complicated, well, not super complicated, but there's some definition, and for rigid things, it's basically trivial. And so then that implies that this FL guy satisfies Milnor excision. So now I can say it's due to U. So this implies that FLI satisfies Milnor excision. And again, it doesn't matter what this means, but what it implies is that I can assume that the V has rank at most 1. Okay, and so that means it has valuative dimension at most 1, and this means that A1 over V has valuative dimension at most 2. And so the cdh topos of A1 over V has has cohomological dimension at most 2. Again, am I allowed to write your name? Good. All right. So therefore, the cohomological dimension of the cdh topos of A1 over V is at most 2. EHIK. Okay, so now I'm trying to prove that something is A1 invariant, and morally speaking, there's only H0, H1, and H2. Now, it's not quite true because motivic cohomology is not concentrated in 1 degree, but it's almost true. Now, how bad can this be, right? It's just 3 groups. Come on. So now we come, in the last 5 minutes, oh my God, to the main argument. So there's no mixed characteristic thing happening today. I'm sorry. So here's the main argument. So I will look at the following guy. I look at KGL mod L. And then I left Kahn extend it, and I cdh-local it. And I guess I look in degree I. Okay? Suppose that this thing is A1 invariant. And I know that this is true if I equals 0, because then I'm just looking at KH. And I want to deduce that then FLI is A1 invariant. Okay, and now if I could do this, then I would win. Because if I take this thing in degree I and I sort of strip off FLI, I get the thing in degree I plus 1. That's how the Motivic filtration works. And so then I will know that it's A1 invariant in degree 0, so FL0 is A1 invariant, so it's A1 invariant in degree I1, so FL1 is A1 invariant, and so on and so forth. Okay, so this will conclude. So what do I do? Well, I will look at the Motivic spectral sequence for A1 over V, and it converges. Well, I will not quite look at the Motivic spectral sequence. I will look at the spectral sequence coming from the filtration sort of this in degree I. So the effective Motivic spectral sequence or something like that. So I will consider the spectral sequence. Okay, and so this spectral sequence will converge, and again, I do get strong convergence because it's just sort of a Postnikov tower thing which tells me the convergence, so some connectivity, and it converges to the homotopy groups of this thing. On A1 over V. And so how does the spectral sequence work? Well, so this has a bunch of homotopy groups which should come out at the end. So there will be a pi I here, pi I minus 1, pi I minus 2, oops, and then there might be a pi I plus 1, and so on and so forth. And now there will be various motivic cohomology groups contributing to this. So here I have, it turns out, of course, the indices are going to be a nightmare. You just have to believe me that that's how it works out. So here you get an HII CDH of A1 over V with coefficients in, well, FL. Okay? And so from now on, I'm just going to indicate which bi-degree you see. So there's an hi plus 1, comma I, and it will contribute to pi I minus 1. There's an hi plus 2, comma I, and it will contribute to pi I minus 2. But there is not an hi plus 3, right? So this is going to be, there's a 0 here because of this cohomological dimension 2 stuff. And it starts in weight I, right? So lower weights would live here, but they are not there. We have removed them. But so here's more stuff. Right? I mean, it also goes in this direction, and there's something here, hi plus 1, comma I plus 1. And here we have an hi plus 2, comma I plus 1, hi plus 3, comma I plus 1, these sorts of things. All right. So now the time is almost over, and I've also almost won. All right. So everything in this column will somehow contribute to pi I. Everything in this column will contribute to pi I minus 1, and so on and so forth. But, of course, there will be differentials. So the differentials, they lower the stem, and they increase the filtration. So there's one obvious differential, for example, this thing here. And there would be more, right? I mean, there could be something like this and whatever. But certainly, there are no differentials which can hit either of these groups. Okay, and also by assumption, this thing here is the same thing as pi star of KGL mod L underline I of V. Well, I know. Well, with this LCDH and whatever. So the point is, it will converge to 0 here. Okay. And so what I learn is that this group is 0 and that this group is 0. So there could be something going on here, and of course there's more groups whatsoever, but certainly I needed these groups to be 0. And okay, so I'm out of time now, but so what I learn is that LCDH L smooth, or no, that FL of I evaluated on A1 over V is connective. And so it turns out that in the connective setting, it necessarily coincides with the H sheafification. So I'm running out of time now, but basically it's given by étale cohomology in this range. And for étale cohomology, one knows, of course, that it's A1 invariant. So I can now compare it with some guy which I know to be A1 invariant, and this will be the end. Okay, so I plan to say too much. And then, so maybe if you give me 1 more minute. So in the mixed characteristic situation, you basically want to do the same thing. You have to replace étale cohomology with syntomic cohomology, and particular syntomic cohomology of general schemes as defined by Barth and Lurie. And then you need, so this rigidity trick doesn't work anymore, and everything else gets much more complicated. But in principle, a very similar argument works, except you get to the very end, where you want to compare with sort of H version of syntomic cohomology. And so this doesn't immediately work, because there's some conjecture which we would like to use, which is called that so-called valuation rings are F-smooth. You look in Barth-Lurie for the definition of that, and then it would be easy. But we don't know this, and so we have to fight for 20 more pages or something to get around the fact that we don't know this. But eventually we can prove it. Sorry for running over. Yes.
Anyways, I wanted to ask, like, somehow now that we know that somehow the Motivic Einberg-MacLane spectrum is always like the slice truncation of the sphere, like somehow that seems to use like everything.
Yes.
Would it be? I mean, like, I was always wondering whether it would be reasonable to take this as a definition and try to like sort of deduce properties.
I don't think that's well. I don't see how to do this. So somehow it's very difficult to compute these slice truncations in any sense of effectiveness. So Mark has showed us how to do it over fields using coniveau. But in general, no, I have no idea how to approach these things. And so it seems more like an accident, right? So who cares about this S0 anyway? So it's very neat, but it's completely useless, I think. So I don't know how to do this, but it would be better, I guess. Yeah, there's nothing.
Smooth maps.
Yeah, yeah.
But in this case, it has.
Right, but
I was wondering if we could somehow like read everything backwards and use it.
I don't see how to do it. I mean, it's some non-explicit thing, and yeah, I don't know how to do it.
In this here and B, if you have, so this is like cdh-local
Mhm.
Bayesian submission bound, yes. If you plug in a regular scheme in there, you'd expect that the Misnevichification suffices.
That is-
there any way to...
That's correct. We can prove this.
You
Yes.
can prove it?
So I can prove it. I mean, you have this like regular J2 or something, so you need to know something about the Gersten complex doing some good stuff. But I mean, under some assumptions, in unequal characteristic, I can prove this. In mixed characteristic, I don't know how to prove this. But you're right. You would expect this to have a stronger statement for regular base, and sometimes we can prove it.
I have a question. So do you have any categorification of this sort of statement which gives you, I mean, a control, I mean, category of coherence with cohomology theory?
I don't think we have an interesting categorification of this statement. I mean, what you can do is you can look at Motivic cohomology not built out of smooth schemes, but out of finite type schemes. And you throw in the cdh topology from the start, and then there's some comparison functor which one can prove is fully faithful, which is equivalent to this miracle that I mentioned in the beginning, that everything has cdh descent. But so for what we did specifically, I don't know what the categorical statement could be.
A more basic question. You said the underlying bullet thing is always a cdh descent.
Yeah.
For free from proper base change.
Yes.
Mind saying a bit more about how that works?
I'm probably going to screw it up. But I mean, it has to do with, you look at the localization sequence between an open and a closed. And so somehow this already suggests that somehow if you make a cdh cover, it's sort of on the open, it's a trivial kind of cover, and on the closed, it's also a trivial kind of cover, and you somehow stick them together. I will probably mess up the details if I try to do it.
Yeah, Tom, I have a question. So what about the S1, I mean the first degree of slice? I mean, S1.
S1. I mean, probably this can also be, I might imagine this can also be approached. So, I mean, there's a general thing that sort of slices don't commute with base change, but in some sense they do commute with base change if the base change is a slice again. So I'm doing this like from the top of my head, so maybe this doesn't work, but generally speaking, so the problem is you could start with a zero slice, you base change it, and it's not even a zero slice anymore. And so basically, if this happens with all of your, if this problem doesn't occur, then more or less it should work, and possibly, right? Because we know that sort of the S1 is built out of things like Motivic cohomology and other things that you understand. So if you could do this over Z, then I think it might be possible to deduce it over general basis using what I said. But I mean, you would have to carefully look at it.
So in the main theorem for Motivic cohomology, is there a chance it could be extended to modules of Motivic cohomology as well?
Well, what would the statement be?
Yeah, just in the statement, just replace Motivic cohomology by any module of Motivic cohomology.
I have not thought, that would be a categorification. I have not thought about this. It's not immediate to me why it would be true. I don't know, sorry.
Yeah, so...
Yes?
So, yeah, you only talk about proving A1 invariance, and so for the P1 spectrum, is it just similar thing, or you
Yes.
have to use P1 and you have also these cohomological dimension bounds?
Yes, it's basically this. It's a very similar structure of argument. I mean, the sort of the degrees that you're looking at shift around a bit, but essentially a similar thing. You do a similar thing. In fact, once you have A1 invariance, you can use GM instead of P1, which is somehow easier for what you want to do. But basically, this kind of game.
Okay, then it's time for a coffee break. Next talk is at 11, but let's